Okay, so we're looking at this next example, and we're trying to see if there's some sort of factorization, s minus a constant type thing. So we first look at s squared plus 4s plus 6. And is there, can I factor it? Is there some way to factor it? It's not. You can try, 5 and 1, 2 and 3. Go through the combinations. That's not going to work. But is there a process that would allow me to create some sort of factorization? And that's where completing the square is going to be very helpful here. So, and I want to focus my completing the square on just these first two set of terms. So if I take s squared plus 4s, I'm going to figure out some magic number that I'm going to add and then subtract, and then I have that 6 I want to take into account. So completing the square says look at the coefficient of the constant, so that's the 4 and the 4s. So 4 divided by 2 is 2, then 2 squared is 4. So if I add 4 and subtract 4, I really haven't changed anything. I've just changed kind of how it looks. But in completing the square, that allows me to write s plus 2 squared plus minus 4 plus 6 plus 2. Okay, so that means that our fraction, and again, I'm going to ignore the inverse Laplace symbol for just a second. But that means our fraction, so s over 2 plus 5/3 is now equivalent to s plus 2 squared plus 2. And so that sort of s plus 2 squared bit, that factorization bit, that's going to motivate me to see if I can manipulate the numerator to have a similar type feel to it. So is there something I can, is there a way to rewrite s plus 2 over 5/3 so that it's something times s plus 2? So let's try that. So let's see, what would I have to do here? So I'd kind of like it to say s plus 2 of some form, and I can see that I am factoring out that 1/2 part. So just kind of let me illustrate what I'm talking about. So I'm looking at this piece, and I'm trying to make that fit the s plus 2 pattern. Now I can't just do that, right? Because it's s over 2. So that means I must have added something, and I have to go back and subtract something. So what did I add? So 1/2 times 2 is 1. So I must have added 1, which means to keep this balanced, I got to subtract 1, and then add that with the 5/3. Okay, so that's 1/2 s plus 2 plus, let's see, 5/3 minus 1 would be 2/3. Okay, so let's put this all together with what we have so far. So I've converted s over 2 plus 5/3 over that s squared plus 4s plus 6. I've now made that look like 1/2 s plus 2 plus 2/3 over s plus 2 squared plus 2. Okay, and this whole conversation was all about that s plus 2 piece. Is there some way that I could manipulate these things to get in that format? Because now that I have it in that format, now I can set it up for my inverse Laplace. So let me do that. So inverse Laplace, I'm going to bring the 1/2 out on the first part, and so that's going to leave me with s plus 2 over s plus 2 squared plus 2 plus, I'm going to bring out a 2/3, and that's going to leave me with a 1 over s plus 2 squared plus 2. Okay, and I claim that if you go look at the chart from inverse Laplace, So I'll kind of speed that part up. And again, we're the plus 2 piece, so the s plus 2, the s plus 2 squared, that plus 2 gets absorbed into the e to the at piece. So it's really, what is the inverse Laplace? So inverse Laplace for s over s squared plus k squared. And that would be cosine. It's cosine of kt. And our inverse Laplace of a constant, so 1 over s squared plus k squared, is sine kt. Okay, so what does that have to do with what we got? So hopefully you can see the mirror that I did here. So we have the 1/2 out front. The plus 2 becomes an e to a 2t. So e to the negative 2t, because it should be s minus, it's s plus, so e to the negative 2t. And then the k in this case is in the 2's position, so what do I square to get 2? I must have squared a square root of 2. So that would be cosine square root of 2t plus, and then we have the 2/3. And that's the same thing. So with the s plus 2 squared, s plus 2 squared would be e to the negative 2t. And then same argument about k would be square root of 2. So sine of square root of 2t. Okay, so it's all about factorization and trying to fit a specific pattern and making decisions based off that pattern.